So today we're going to start our unit on acids, bases, and salts. This is going to be a pretty intense unit with a lot of information, so you're really going to want to take good notes, re-watch these PowerPoints, and keep up with all the work and ask questions as we go along. We're going to start with some theories on acids, and one is the Arrhenius theory. Acids, bases, and salts conduct electricity when dissolved in water. That means they're electrolytes. We learned this earlier when we did the test with the light bulb, where we put things that conduct electricity that break into ions, and they're able to transfer that electricity to complete the circuit and light the light bulb. Acids are substances that ionize in water to produce hydrogen ions, which are just a fancy way of saying protons, and our hydrogen ions are going to be H+, or H+1. Bases are substances that ionize in water to produce hydroxide ions. That's our OH-1. And that's going to be very important through this whole unit. Salts are substances that ionize in water to produce something other than hydrogen or hydroxide ions. Our most common salt is NaCl, and when it breaks into pieces it forms Na+ and Cl-. Whenever you have your hydrogen ion or your hydroxide ion, it has some other counterpart that brought it there. It's not just a hydrogen ion. So if you're looking at something like hydrochloric acid, there's going to be the chlorine there. If you're looking at something like sodium hydroxide, there's going to be the sodium ions and the hydroxide ions. Some examples of Arrhenius acids and bases. One we were just talking about, hydrochloric acid. When hydrochloric acid is put into water, notice here it's a gas, and then here it's aqueous, which means it has gone into water. It becomes H+, which is that proton, and then Cl-. If we look at sodium hydroxide, the other classic example of a base, notice it's a solid to start with. We put it into water, it becomes aqueous, it becomes Na+ and OH-, forming that hydroxide ion. Bronsted-Lowry came up with a slightly different theory that helps explain some of our other definitions of acids and bases. They're not quite as obvious as our Arrhenius acids and bases, but they're not too far off. They redefine the terms acid and base to be an acid as any substance that donates a proton during a chemical reaction. If we look back here, the example we just had, donating a proton. A base is any substance that accepts a proton during a chemical reaction. So something that's going to take that hydrogen in. And you'll see that that's another way that we can define an acid and base. The most common example of that is ammonia, and we'll take a look carefully at how ammonia works. So here's some examples. We have HCl, and we're going to add it to water. And by adding it to water, we're going to form H3O+, which is called the hydronium ion, and we're going to see that a lot. Basically, it's a water with an added hydrogen. It's just a different way of writing that HCl with just that hydrogen by itself. A lot of times we have this H3O+, and then Cl-. We can also reverse that same equation and say, okay, well, we have this H3O+, which is that hydronium ion. We combine it with chlorine, we're going to make that hydrochloric acid back, and then also make water. We're going to have the reverse of that reaction. There's some terms that we need to look at. It's a conjugate base and a conjugate acid. A conjugate base is the particle that remains after the proton has been released by the acid. Let's think about that. The particle that remains after the proton has been released by the acid. We know that hydrochloric acid is our acid. So the particle that remains after the proton has been released. Here's the proton and the particle that remains. First of all, a conjugate base is always found in the products, which is the right-hand side of the equation. It's never, ever, ever found in the reactants. The particle that remains after the proton has been released. Here is my proton. The particle that remains is my Cl, and so that's going to be my conjugate base. The conjugate acid is the particle that is formed when the base acquires a proton from the acid. In an acid-base reaction, we always have to have an acid and a base in the reactants. So if this is obviously our acid, H2O is going to act as our base. H2O can act as either an acid or a base, as we'll see. The particle that is formed when the base acquires a proton. If this was our base, now it has acquired this proton, it has an extra hydrogen, and so this now is our conjugate acid. If we take a look at this next example, the only thing that can be an acid here has to be our H3O+, because it's the only thing with a proton, which means our Cl- is acting as a base. To find on the product side, the conjugate base is the particle that remains after the proton has been released. My proton was here, my proton has been released, H2O is now my conjugate base. My conjugate acid is the particle that is formed, okay, when the base acquires the proton. Here's my base, it acquired a proton, this is going to be my conjugate acid. It doesn't always mean that conjugate acid is written first, it just happens to be that in this example. We've already learned how to name acids, and so I'm going to go through this very quickly as a quick review, but you may pause the slide in case you have any questions. You are definitely going to be responsible for just naming acids in this unit, but we did this all the way back in the beginning of the year. Binary acids contain only two elements. This is when we use the prefix hydro and the suffix ic. Okay, two elements meaning no oxygen. Our binary acids do not contain oxygen. An example is hydrochloric acid. Our ternary acids contain three elements, and this is where that oxygen comes into play. We sort of broke it down into two simpler groups, although this slide will break it into four. It doesn't make it any more difficult. The most common form of the ternary acid is given no prefix and the suffix of ic. So something like HClO3, and we learned that it's the 8, the most common form, so the 8 becomes ic. If a second acid is formed containing the same elements but fewer oxygen atoms, the suffix is OUS. And so this was our ite, became OUS. And this breaks it down and adds into the, and so chlorous acid, which is chlorite. If we're looking, and this only deals with our chlorines, if we have hypo, and we just learned that as it being the hypochlorous acid, so the hypochlorite ion we just called hypochlorous, so we didn't add a separate rule for that. And then the same thing with per, for perchloric, we knew it was perchlorate, and so we just changed that 8 to an ic. So these two rules are sort of superfluous. We don't really need them because they're already covered in the 8 to the ic and the ite to the us rules. So identify the conjugate acid-base pairs in each of the following. Nitric acid and sodium hydroxide produce sodium nitrate and water. You're going to be responsible for predicting these products, but we're going to start with giving them to you. Nitric acid, and I would go ahead and pause this recording and make sure that you can write that reaction, and then come back and check it. So take a second and pause. Okay, let's see how you did. Nitric acid would be HNO3. In fact, actually, I can put all three of our reactions up. And so why don't you go ahead and pause it now. Do all three of them, and then we'll go over all three. Okay, so now we'll go over all three. Nitric acid, HNO3, and sodium hydroxide, NaOH. And if it helps you, you can always make your little notes, Na plus 1, OH minus 1. Produce sodium nitrate. Na is plus 1, NO3 is minus 1. And water. And look at that. I check and see if it's balanced. It is. Okay. This has hydroxide. This is obviously going to be my base. This has hydrogen, so this is my acid. This is my base. And we're identifying the conjugate acid-base pairs. And so if we go back to our definitions all the way back here, your conjugate base is the particle that remains after the proton has been released by the acid, and your conjugate acid is the particle that is formed when the base acquires a proton from the acid. So back to this slide. So if I get rid of this proton, my NO3 is what's left. This is what's going to be my conjugate base. My conjugate acid is the particle that's formed, that acquired that hydrogen, That's going to be my water, which is really HOH, okay, if that's easier to look at. Sodium bicarbonate. Oops, that two didn't move. Oops, which is sodium bicarbonate is sodium hydrogen carbonate plus hydrochloric acid, which is going to make sodium chloride, and carbonic acid. Let's check and see if we're balanced. It looks like we are. I have two H's, I have a carbonate, I have sodium, chlorine, looks good. Okay. My acid is going to have my hydrogen in it, HCl. This is going to be my base. This is going to be my conjugate acid, because the particle that's formed when it acquired a proton, which it did, acquired this proton here. And this is going to be my conjugate base. Ammonia is NH3 plus the hydronium ion, H3O plus, is going to produce the ammonium ion, NH4 plus, and water, H2O. This has my extra hydrogen here. This is going to act as my conjugate acid. My acid. This is going to be my base. Ammonia is always going to be your base. This acquired the hydrogens. This is my conjugate acid. Water here is going to be my conjugate base. Now, let's move on to this last part here. Reactions with acids. There's three basic ones. Acids and metals produce salts and hydrogen gas. That's the first one. So hydrochloric acid and magnesium. We just did this lab. Hydrochloric acid plus magnesium will make, I always think it's easier to do this first, hydrogen gas, which is H2. That's always your first product. Plus what's left. I have Mg, which I know is plus 2. Cl is plus 1. So it's MgCl2, which is my salt. I go back in and balance it. That's my first type of reaction with acids. My second type of reaction with acids and carbonates produce salt, carbon dioxide, and water. And so my example here is hydrobromic acid, HBr, plus calcium carbonate, Ca is plus 2, CO3 is minus 2. It's going to produce a salt, carbon dioxide, and water. Again, I think it's easier to always list these ones first, because it's always there. CO2 plus H2O, and then I sort of look and see what's left. I have Ca and Br left. Ca is plus 2. Br is minus 1, so it's CaBr2. I'm going to need 2 of these. That's going to balance my 2 hydrogens, and it looks like everything else is balanced. Acids and bases produce salts and water. Hydrochloric acid, HCl, plus sodium hydroxide are 2 most common examples. I like to start with that water, because that's my definite, and I know what it is. And then I look and say, okay, I have Na and Cl. So there's my salt. And we will be practicing with all of these in class. And the very last thing that I need you to do is to memorize the 6 strong acids. These you need to know. HCl is hydrochloric, HBr hydrobromic, HI hydroiodic. Notice HF is missing. It is not a strong acid. H2SO4 sulfuric, HClO4 perchloric, HNO3 nitric. You're going to need to know these to be able to do problems in this unit. So just go ahead and commit those 6 to memory. These 3 are pretty easy because they're right in a row in the periodic table, as long as you leave out fluorine, sulfuric, perchloric, nitric. Make sure you know those because they will definitely be showing up on tests and quizzes.